Hello, uh, I'm glad you are interested in this project. I would like to thank giving me opportunity to present in 73rd annual meeting of the ABS Division of Fluid Dynamics Geographical Fluid Dynamic Oceanographic session. My name is Sudam Surasinghe. I'm collaborating with Sathsara Dias, Kanaththa Priyankara, Erik Bollt, Marko Budisic, Larry Pratt, and Sanchez-Garrido. This project is about dynamic mode decomposition, also known as DMD algorithm. We are demonstrating how to apply that algorithm to oceanographic data. Here we are use the data from Strait of Gibraltar to demonstrate the DMD algorithm. Strait of Gibraltar and Western Mediterranean has a lot of interesting features. Such features are Atlantic jet, Western Airborne gyre, and dynamics around the canal sill, like internal waves, tidal, internal tidals, and so on. So let's zoom into those features. We are interested in Western Airborne gyre, some internal wave patterns. This is a satellite image of such wave pattern, and this figure shows the propagation of that wave trend. We want to recover or decompose those features from the given data set, and how we deal with that, we are using DMD algorithm. We are applying DMD algorithm to the data set, and we want to decompose or isolate those features. So let's talk about the simulated data. These are the input data for our algorithm. The simulated data simulated by MIT general circulation model, that is a 3D finite volume model. And in this, or the DMD algorithm or the DMD calculation, we only use the velocity component. And in that setting, or that numerical model, they use the tidal force diurnal O1 K1 and semi-diurnal M2 S2. The grid is shown like this. Grid selected as these two, or the levels, or the depth levels. We have 32 depth levels, and the surface, we have a grid with the collinear orthogonal grid, and it has 190 times 96 grid. And we selected 6 days of data, or the 144 hours of data to feed into the DMD algorithm. So let me talk about the DMD algorithm. Why DMD algorithm? Why is this useful in this kind of analysis? DMD algorithm can isolate specific dynamic structures, such as we are looking for the gyres or the internal waves, periodic patterns. Then the next important thing is we can either use numerical data or the observed data. This is an equation pre-model. We don't need to know the equations here. So other important feature here is we can use or the predict or the interpolate data by reduced dimension model. We can use a few modes to predict or the interpolate the data. This is a very simple algorithm. You can use the MATLAB with the 5 line of code to implement this algorithm. But this is a very powerful tool because of the Koopman analysis. This algorithm is justified. We can justify using the Koopman operator. So let me give you a little bit more detail about what this algorithm is. This algorithm separate the data model into a spatial profile and time profile. Specialty here is DMD modes oscillate at single time frequency. which means we can isolate the mode by frequency. First, we get we are ranking this. We can rank these modes by large, mean, L2 norm, or the L2 contribution. Then we can categorize those modes, or we can isolate, or we can check those modes with the eigenvalues. If you have a positive real part, then that modes are growing modes. If you have a negative real part, that means a decaying mode. Also, we can use the imaginary part of those eigenvalues to check the periodicity or the period of those modes. For example, in here we have the original data set. We have a lot of features there. We want to isolate some features like in tidals. For example, if you want to isolate the semi-diurnal tide, we will check the mode or the eigenvalue frequency of the imaginary part of the eigenvalue for the period. We can calculate the period using this formula, and then we can compare that period with the tidal period. Then we can find the dominant semi-diurnal mode. In that mode, we can see such some tidal patterns, or the diurnal mode, and so on. So basically, we have a lot of features in the data. Then we can use the eigenvalues to isolate some special features. So that is the very powerfulness of this algorithm. So we can use the real part of the omega values to think about the decaying and growing features, and as we discussed before, we can think about the periodicity if you have the imaginary part. If you have imaginary part, then we have periodicity. A real part, if you have a real part, then we have a negative real part, it is decaying. If you have a positive real part, then it is growing. So the payoff for this algorithm is comparing to the POD algorithm, the mode selection process. It is depending on the application. I can talk about this. If you have any questions, feel free to stop by in the allocated time. So let's discuss more about DMD algorithm which apply to the Gibraltar data set. In this figure, these two figures shows the spectrum and the ranking. The left figure shows the ranking of the modes. We rank using the L2 norm contribution, and then we can further discuss about the mode using the decay rate and frequency. Almost all the modes are decay mode in this scenario, and if you see these red dots and blue dots, if you increase the number of selected mode, we can get into some other mode, but sometimes it might be a harmonic of the first selected mode. So let's zoom in this. This table shows the detail about each mode, like half-life time and period and L2 mean contribution and the magnitude. Then this figure shows the detail about the half-life time, or the compare this with the original time length we consider. We can see some of the mode has a big half-life time, which means it is slowly decaying. Some of the mode has low half-life time, which means it is decay very fast. And when we are thinking about the what are the modes, it has the decay rate lesser than, or the half-life time more than the data set we had, most of them are physically meaningful modes, like semi-diurnal mode, diurnal mode, and some harmonic of those modes. Those modes has the bigger half-life. So we consider those modes here because we want to isolate such relations, like tidals or the internal waves. All those has some related to the tidals. The first mode, that is a background mode, which means it stays in entire time, and the period, which means the period is infinity, or the frequency is zero, or the real part, the imaginary part is zero. The second important mode here is the semi-diurnal mode. That period of that mode is equal to 12.32, and it has very big half-life time, which means it is persistent in this case. And next interesting mode is diurnal mode, the mode which has a period 24.65, and it half-life time also bigger than our data set, which means there is also persistent mode. And there are a couple of other modes we were interested, some like harmonic of the diurnal mode and harmonic of the semi-diurnal mode. Those also has a bigger lifetime, bigger half-life time. So let now move on to each mode. First, we will talk about background mode, or the mode 1. That is a non-oscillatory mode or background mode. It is stay entirely in the that time period. So this shows the speed profile in the surface speed profile. We can identify those Atlantic jets and gyres and hydraulic transitions in this mode. These hydraulic transition, Atlantic jet, and Western Alpine gyre are very well-known features, but we also can identify another interesting feature here that is not much known, the less known feature, the secondary gyre. So this is a new interesting feature we found in this case. This is stays in this entire time, or the 6-day period. We can see that same things, same features to get the cross section, and we can justify using that cross section as well. Is hydraulic transition, and there are some hydraulic jumps as well. And we can also identify the exchange flow in this case. So now let's move on to the other interesting mode. First, let's talk about semi-diurnal mode. This mode is persistent, and this mode has a very big half-life time, which means effectively no decays. And it we can notice that it reveals the internal waves here, and radiation of internal waves radiating from this straight into the Mediterranean. Next, let's move on to the second harmonic of that semi-diurnal, that further give the detail about that internal wave. We can clearly see the wave packets in this mode. This is the second harmonic of that semi-diurnal mode. This is also a persistent mode, and if you see the pace of this mode, we can clearly see that wave packets. Now, this is the most important mode that we found because it reveals few interesting features. One interesting feature is this band of alternating band in here, this surface plot. This is we can identify this as a meandering mode, and we want to hypothesize that as a meandering origin from the tidal pulse of viscosity generated in the strait and then carried by the jet. This is a interesting feature we identify. This is a not known feature until now. I think this is the first time such a feature found, and we think that is these meandering modes, meanderings originated from that tidal pulse. And next important feature that is also less known, these Kelvin waves, that coastal trap Kelvin waves, that is also seen in this video. Those are the two interesting features we identified in this analysis. We can further clarify that when we're looking at the cross section. We can see those bands are very narrow here. It is not gone deep down. So that tells us there is a meandering mode. Okay. We can further emphasize that when we are considering the harmonic of the semi-tubular, we can see the detail about that meanderings, and also we can see that generating of the internal waves as well, and flow of the internal waves. So let me summarize the details here. So dynamic mode decomposition decomposes the data into the world according to the single frequency. So which means we can isolate the interesting features by the frequency. In oceanographic data, in this case, we can isolate the tidal patterns. So that is a very interesting feature we can use from dynamic mode decomposition. Then clear time signature enable easy correlation with the tidal component and identify the tidal harmonic. Then we show that individual dynamic mode correlated with specific features and mechanics in the oceanodynamics, such as Western Elbow gyre, Atlantic jet, hydraulic transition, and radiating internal waves. So next thing is we can use this algorithm to further and identify some hidden features or the less obvious features like secondary gyre and the hydraulic jump and meandering at the Atlantic jet and Kelvin waves. So these are the references we use, and thank you for your attendance, attention. And if you have any question, feel free to stop by in the available time slot. And thank you very much. See you there.